Every day, enterprise systems quietly generate an avalanche of business documents, from client invoices to complex financial reports. But under the hood of these automated systems, the code responsible for assembling these pages often relies on raw, low-level drawing APIs. These are imperative systems. They force developers to write explicit instructions for every visual element, specifying exactly where to place a piece of text or draw a line using hard-coded X and Y coordinates. This approach is deeply fragile. Injecting a single new paragraph can displace every element below it, breaking the layout of a 50-page report and requiring manual coordinate recalculation. Teams often try to patch this problem with XML-driven template engines, but those usually result in rigid workflows that are equally painful to maintain and update. Instead of optimizing coordinate management, we can shift to a semantic layout engine. That is the specific architecture behind a project called GraphCompose. Modern enterprise software needs a declarative engine that separates the actual meaning of a document from the mechanical process of drawing it. GraphCompose approaches the document generation process from a completely different angle. It uses a declarative API. Instead of telling the computer where to put pixels, developers describe what the document actually is, defining sections, paragraphs, and tables. The engine acts as the computational brain sitting between your raw data and the final compiled file. To understand how this works, we can trace the execution pipeline step by step, from the initial Java code all the way down to the final binary output. Removing the manual math allows the document generation process to function as a deterministic system rather than a series of manual layout adjustments. The pipeline begins at Layer 1, the authoring layer, powered by a fluent Java DSL. Here, developers map out their business logic using high-level structural primitives, assembling layer stacks and defining global theme tokens. When that code executes, it generates Layer 2, the semantic document tree. The engine perfectly understands the hierarchical relationship between every element, but it lacks one crucial piece of information. There are 0 physical X or Y coordinates stored in this tree. Traditional drawing APIs demand placement instructions immediately. They force you to place the roof before the walls are fully measured. GraphCompose intentionally delays coordinate calculation. The system must understand the entire logical structure before it can successfully resolve complex page layouts. That resolution happens in Layer 3, the layout engine, which serves as the mathematical core of the architecture. The engine ingests the coordinate-less semantic tree, calculating physical space using a strict 2-pass mechanism. The first pass measures the dimensions of every element. The second pass locks them into alignment, resolving table cell sizes, z-index layers, and automatically calculating exact page breaks. Isolating this complex calculation achieves complete determinism. Because the layout is a pure function of the semantic tree, feeding the engine identical data produces the exact same pixel-perfect layout every single time. This allows development teams to run layout snapshots through standard unit tests, catching visual regressions long before a file is ever generated. The layout engine operates as an autonomous typesetter, absorbing the entire cognitive load of physical space management. Once the math is complete, the engine outputs Layer 4, placed fragments. A placed fragment is an exact hyperspecific geometric instruction. These fragments come in precise structural types: a placed text string, a placed rectangle, a placed line, or a placed image. This marks the crucial threshold where abstract meaning has been fully converted into absolute geometry. At this stage, the placed fragments are completely agnostic to the final output format. They serve as a universal intermediate language. The code that calculates the layout is completely severed from the software that ultimately draws the file. That final drawing step happens in Layer 5, the render backend. Currently, GraphCompose uses PDFBox as its primary production backend, mechanically executing standard PDF draw calls. By routing the identical fragment data into a PDF binary or an SVG file, both formats function as fixed layout vector canvases. To support SVG, the backend merely translates the universal geometry of a placed fragment into the corresponding XML tags. This fixed layout approach is very different from flow-based formats like Microsoft Word's DOCX. DOCX is architecturally hostile to this system. It demands editable, flow-based rules that actively fight against pre-calculated fixed bounding boxes. By deferring the final visual execution to interchangeable backends, a single layout logic structure can seamlessly power entirely different presentation technologies. Looking at the GraphCompose semantic model reveals the practical outcome of this architecture. For the developer, this deep structural logic translates into a system that is cinematic by default. Complex design elements like soft-colored panels, accent strips, and nested table layouts are natively supported primitives, not brittle workarounds. Global visual themes and styling rules are tokenized and managed directly by the engine itself. A semantic engine automates the layout math and makes advanced visual design scalable across massive enterprise applications. GraphCompose introduces an intermediate architectural layer that permanently decouples the business logic of a document from the mechanics of rendering it. This decoupling unlocks a range of future applications, from generating lightweight PNG thumbnails to rendering HTML canvas previews, or even assembling PowerPoint slide decks. By treating documents as semantic trees rather than raw coordinate maps, GraphCompose provides the necessary foundation to elevate document generation from a tedious script into a true